In this video, we're going to cover sound and resonance, which is Unit 8.1. So starting off, these are the main formulas for this unit. Some of the more notable ones are the formulas for the Doppler effect, beat frequency, and wave equation, which are the last three on the list. A wave is a transfer of energy in the form of a disturbance, and it's usually through material, substance, or a medium. And something important to note is that movement does not make a wave, but rather it makes a pulse, and to make a wave you need at least 2 pulses. Here we have a diagram of a wave, and you can see where the crest, the trough, and the amplitude are, as well as the wavelength, which is the distance between 2 crests or 2 troughs. When it comes to reflection of waves, there's both fixed end reflection and free end reflection. So when you send a wave toward a fixed end, it will return on the opposite side of the rope, as is shown in the first diagram on the left. But if the end is free, then the wave will return on the same side as the original wave, which is the diagram on the right. Standing waves are 2 identical waves traveling in opposite directions. As shown in the diagram, a node is a point on a standing wave with an amplitude of 0, and an antinode is a point on a standing wave where the amplitude is at a maximum. And the distance between 2 nodes is wavelength over 2. One thing to keep in mind is that when a standing wave is in a tube, the length will change depending on whether or not the tube is open at both ends or closed at one end. For example, when the tube is open at both ends, the first harmonic is 1/2 of a wavelength, while in a tube that is closed on one end, the first harmonic will be 1/4 of a wavelength, and that's shown in the diagram in the first row of pictures. When waves cross, their amplitudes add, and this is known as the principle of superposition. However, once waves get past each other, they retain the shape they had originally. There is both constructive and destructive interference. The first picture shows constructive interference, and this is when the waves add to form a larger wave. And then the second picture is destructive interference, which is when the waves cancel when added. The 2 main types of waves are transverse waves and longitudinal waves. And longitudinal waves are also called compressional waves. Transverse waves are when particles vibrate at right angles to the direction of motion, while longitudinal waves are when particles vibrate parallel to the direction of motion. And an example of longitudinal wave is sound.
In a longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels. Longitudinal waves are also referred to as compression waves. In a transverse wave, the disturbance that makes up the wave is perpendicular to the direction in which the wave travels.
The next topic is overtones, harmonics, and octaves. The first picture is supposed to represent a wave in motion. It's as if the ends are the nodes and the top and bottom of the oval represent the wave moving up and down. The fundamental frequency is the first time you get a standing wave on a string, like the first picture, and this is 1/2 of a wavelength because the distance between nodes is 1/2 of a wavelength. If you double the fundamental frequency, you get a whole wavelength, which is what the second picture represents, and this would be the first overtone or the second harmonic. Then the second overtone, or the third harmonic, has 3 loops and is the length of 1.5 wavelengths.
Now when it comes to musical instruments and musical notes, this natural frequency mechanical resonance, if I took a guitar string and plucked it, I'd get what's called the fundamental note, the note I hear when I play the guitar, and we call that the first harmonic. Now I can make another note with that string. This is the string vibrating up and down. If I take a guitar and put my finger somewhere in the middle of that wave and then pluck the string, I hear something that's 1 octave higher. And what we call that is the first overtone, or the second harmonic. That's when the string is vibrating like this. This side's vibrating up and down, this side's vibrating up and down, but nothing's happening here. We call that a node, and we call this an antinode. If I put my finger in a different place on the guitar string, maybe 1/3 the distance from the nut to the bridge, and pluck it, I get this kind of pattern. And it sounds like a little bit higher note again. And so this is called the second overtone and the third harmonic. So this is the natural frequency of the wave. I can make the wave vibrate in different modes though.
Also in this unit was the Doppler effect, which is represented by the equation at the top of the slide. As you can see in the equation, there are plus and minus symbols. So you use plus when the source is moving away from the observer, and you use minus when the source is moving towards the observer. And essentially the Doppler effect is just saying that as the source of sound gets closer, the frequency increases. F2 is the frequency heard by the observer, while F1 is the frequency of the source. And then V is just the velocity of sound in the medium, Vs is velocity of source, and Vo is the velocity of the object. And if you remember, this was the discussion where we talked about the race car and how as it gets closer to you, the sound you hear changes because the frequency changes.
Alright, this is how the song really goes, okay? Okay, go. Oh, shit.
Everything has a natural frequency. When something is pushed at its natural or fundamental frequency, resonance can occur. This can lead to a good thing, such as musical instruments or tuning a radio, or bad things such as bridges collapsing and glasses shattering. A sonic boom is the sound that results when an object travels through the air faster than the speed of sound, generating shock waves and a large amount of sound energy.
Problem 1 states, the figure above on the left shows a uniformly thick rope hanging vertically from an oscillator that is turned off. When the oscillator is on and set at a certain frequency, the rope forms the standing wave shown above on the right. P and Q are 2 points on the rope. So part A is basically asking us why the tension of point P is greater than the tension of point Q. To help us understand why point P would have more tension, we need to draw a free body diagram that shows the force of gravity and the force of tension. So the force of gravity is equal to mass times the acceleration due to gravity, which is a constant 9.8 meters per second squared. And because rope has mass and P has more rope under it than Q does, P is going to have more tension because the force of tension is equal to the force of gravity. So P has more mass below it pulling it down, and that's why it has more tension. Part B says, a student hypothesizes that increasing the tension in a rope increases the speed at which the waves travel along the rope. In a clear, coherent paragraph-length response that may also contain figures and/or equations, explain why the standing wave shown above supports the student's hypothesis. So first thing we need to answer this problem is a topic sentence. Increasing the tension in a rope increases the speed at which waves travel along the rope. And we know that speed can be calculated using the formula V equals F wavelength. Because the wavelength is longer at the top of the rope, and as we learned from the previous question, the force of tension increases the further up the rope the point is. We know that wavelength and tension are directly related, so as wavelength increases, tension also increases. Furthermore, we know that velocity increases as the wavelength increases because the frequency is going to be the same for the entire rope because it's determined by the source. And we know that tension increases as wavelength increases, so therefore velocity increases as tension increases. Question 2 states, the figure above shows a string with one end attached to an oscillator and the other end attached to a block. The string passes over a massless pulley that turns with negligible friction. 4 such strings, A, B, C, and D, are set up side by side as shown in the diagram below. Each oscillator is adjusted to vibrate the string at its fundamental frequency F. The distance between each oscillator and pulley L is the same, and the mass M of each block is the same. However, the fundamental frequency of each string is different. Part A asks, what is different about the 4 strings shown above that would result in their having different fundamental frequencies? Explain how you arrived at your answer. The linear mass density of each string is going to be different. This is because for the first harmonic, L is equal to wavelength over 2. So, because L is given to be the same for all the strings, the wavelength must also be the same. V is equal to F wavelength, and because F is changing while wavelength stays the same, we know that V is also changing. They give us that V is equal to the square root force of tension over M divided by L. Force of tension is the same for each string, so the M divided by L must be changing for V to be changing. Part B says, a student graphs frequency as a function of the inverse of the linear mass density. Will the graph be linear? Explain how you arrived at your answer. So we know that somehow we have to get F and M divided by L in an mx plus b format. In order to do this, we want to set the equations V is equal to the square root force of tension over M divided by L equal to V is equal to F wavelength. So we will get the square root of force of tension over M divided by L is equal to F times wavelength, and we want to put this into y equals mx plus b format. We can do this by rearranging the variables to get F is equal to the square root force of tension over wavelength times 1 over the square root of M divided by L. Because F is a function of 1 over the square root of M divided by L instead of 1 over M divided by L, it will not be linear.